Done. Yeah.
Just a minute.
Sure.
Yeah. We are good. For dummies, yeah.
Yes, we are recording.
Okay.
Yeah, looks like it's recording. Great.
Okay.
Good to go?
Yes, yes, please.
Awesome. So yeah, DK, thanks for the intro. Again, an old bio, but happy to see a younger self, as I said before. Yeah, I'm Matt Williams. I'm a CTO of Rockport Networks. Really appreciate people's time to attend the session today. Going to be talking about some of the architectural details behind Rockport Networks and what makes it well suited for large-scale AI HPC systems, really focused on scale and maintaining performance. So we'll go through some of those details today. So Rockport itself, it's all about distributed networking. We have an embedded switchless architecture, very different from traditional networks where you'll have centralized layers of switches. And we're very much focused on the performance intensive compute market, AI, ML, and HPC. We have sales worldwide. We have North American and EMEA centers of excellence. There's over 20 switchless networks deployed today. And as a company, we have over 85 issued patents. A little bit about us. So I'm going to make a bold statement here, but we believe the network is the problem these days. So the performance boosts in this on the compute side, CPUs and GPUs have been phenomenal recently. And on the storage side, again, great advances in performance. So what's happened is the network has become the bottleneck, and it's throttling compute and storage. It's leaving some of those resources idle while they're waiting for data or messages to be delivered. And this problem is exacerbated at scale. So we've taken a look at some of the results our customers have seen, and there's a few facts here that are pretty shocking. So traditional spine leaf architectures can dilute the effective bandwidth by 68%. So you may think you have a certain bisection available to you, but in practice, the realistic effective bandwidth is much lower than that due to the way in which that bandwidth is made available to flows. And that means the network can degrade network workload performance between 20 or 30%. So a workload due to the bottleneck of a network will take longer to run. And that means, of course, if a workload's taking longer to run, it means it's waiting for data, which means those resources are idle, which is, of course, very expensive. So Rockport does have a different kind of architecture, a distributed architecture, where instead of having centralized switches, the switching function is moved to each of the endpoints. So each of the nodes in a Rockport network contains what we call a network card that contains both the host side and the switching functionality. And in our solutions, our nodes actually have 12 direct connections to other nodes. And again, no external switches. So in our architecture, it's a very different looking beast. Nodes directly connected to those 12 other nodes, we form a rich mesh topology. We create very rich number of paths, very high path diversity. And because the switching function is distributed, we have unique capabilities compared to other high performance networks. Now, even though it's a very different looking network, we've made sure that it's very easy to adopt. So we have a standard high performance Ethernet-based host interface supporting RDMA, verbs, offloads, TCP, UDP, all the things you'd expect. We are supported by all MPI libraries, all parallel programming models. And we have some pretty advanced capabilities. Again, going to go into the details. We have per packet adaptive routing, advanced congestion controls. And almost most importantly is we've ensured that the critical messages that drive workload completion time are immune to congestion. And because the switching function is distributed to the endpoint, we scale a lot better than centralized infrastructures where additional layers of switches may be required. So again, very much focused on the performance intensive side of the market. So the physical manifestation of our solution, the main component, and it's the only active component in that solution, is the network card. It goes into a server node or a storage node. It looks like a high performance Ethernet NIC. So from a software standpoint, existing drivers, existing software stacks, it all just works. It really is plug and play. But we also have there a field upgradable FPGA that runs something we call RNOS. That's our Rockport Network Operating System. And that's what implements a Rockport network. We'll go through some of the details of what it does. And so again, another layer of the onion, exactly how it works and why that's beneficial for applications. And out of this network card, we have 12 independent links. each carrying 25 gigabits per second, for an aggregate of 300 gigabits per second of fabric per node. And those fiber optic cable is plugged into a device we call a shuffle. And what that does is break out the 12 links from the cable and distributes them to other nodes. 6 of those links go to nodes typically within the same rack. And then most importantly, 6 of those links create direct connections between racks. So in a Rockport environment, the network distance, the average network distance in a rack or across the entire cluster is actually near equivalent, which means there's much more flexibility in workload placement. And all the shuffles and all the cables that join them are completely passive. So that allows us to scale in terms of power consumption very linearly. You don't have to worry about additional layers of switches. The card is one per node. And then in order to help people scale codes, understand how the network is performing as you change the code to get it to larger scale, we provide deep insights through the Autonomous Network Manager. We pull lots and lots of stats out of every part of the network, and not only do we visualize them and show them live, but we store all those statistics for a full 7 days. So typically our customers will run a code, they'll go back and look at the job performance and see, well, what kind of network traffic was being generated by that job? Sometimes computational scientists don't really know the impact of a code change to what happens on the network. So we provide that insight to allow people to tune codes and get better scalability of their codes. So RNOS runs on that FPGA within the network card, and it does several very important functions. The first is it does a self-discovery function. So here in the top right-hand corner, I guess I could use my mouse, I'm showing a simplified direct connect architecture like ours with only 4 links per node, just to make it a simple diagram. So the first thing that happens when a node is added to the Rockport network is we discover all of our neighbors, so sort of a hello message. And once that occurs, a link state routing algorithm runs on the whole topology, and every node ends up with a complete map of the network. And then we run our deadlock-free routing algorithm. What this does is create a full set of paths to every destination that are physically independent and deadlock-free. So here we're showing an example of a source node in a distributed way, creating routes to this known destination. First thing it does is pick one of its egress ports, it does a shortest path calculation to the destination, and then it'll take the next egress port and do the same thing, ensuring that, in this case, the blue links aren't used again. So we end up with a set of 12 physically independent routes, no common links, and an important reason for that in distributing load and avoiding hotspots. And then we take the best 8. So in a direct connect architecture, some of the paths can be longer than you want in terms of latency and per hops. So we remove the ones that are too long. And as traffic is moving from every source to every destination, we spread it across those 8 paths that we've generated. And that's in order to avoid creating a hotspot, as well as to react adaptively on a per packet basis when congestion does occur within the network. And the other unique thing about Rockport is, although we look like Ethernet and Ethernet frames are generated within the nodes, the first thing that we do is we segment those packets into flits. These flits are variable size between 64 and 160 bytes. And those flits contain in the head flit the route to get to the destination. So again, source routing, the full route to get to the destination is within that head flit. And then the embedded switching, the flit switching within each of these nodes will then follow that route vector through the network. And so there may be a forwarding node allowing traffic to move to the destination node. The flits are then reassembled and the original Ethernet frame is delivered. So although we look like Ethernet, the switching function, the routing function, the topology discovery, all the things that may be familiar with in the Ethernet world, we don't use those. We take the best of the host side parts of Ethernet, and we replace the way in which you move the traffic. And that gives us some advantages. We're natively lossless. We're predictable low latency at scale. So one of the key differentiators with Rockport is we have adaptive per packet multipath routing. So here we're showing a high-level diagram of what it looks like when a source and a destination nodes are using our adaptive multipath routing. So we'll have one or more RDMA flows, queue pairs, going between a source and a destination. They will, of course, generate network traffic, some packets. And those packets we distribute in a round-robin way across the 8 parallel paths that we've pre-calculated. And again, because these have no common links, we actually have an aggregate bandwidth available to us of over 200 gigabits per second. And because those paths have differing latencies due to their lengths or the congestion along the way, those packets are almost guaranteed to arrive out of order. And that can be detrimental to some transports. So what we have is a packet reordering function at the destination that will take those packets that arrive within our card out of order and then put them back into order before delivering to the host. That way, all transports can be used, whether they're connection-oriented or whether they're datagram-oriented. And we have 8 paths today. As we're designing our exascale solutions, we'll actually be making use of at least 16 parallel paths through the infrastructure. You'll see in the next few slides that gives us pretty strong advantages as you get to very large scale. So a little more detail on how this works. So first thing that happens at the source node is we have some heuristics. Because what multipath routing is really good for is bandwidth sensitive traffic. Think of AI, ML, think of IO. It's when you have a long-lived heavy flow of traffic, because what you're wanting to do is optimize for bandwidth performance. So we look to make sure we're optimizing the use of multipath when it makes sense. And customers or end users can also enable or disable this capability at runtime on a per job basis. So for a priori knowledge of the kinds of traffic being sent, they can simply say, yes, I want multipath, or no, I want to be latency focused. And then there's a weighted round robin per packet distribution of those packets. So when we first start out, it's evenly spread across the 8 paths. But as we monitor the paths in the far end, we're monitoring the arrival time of the packets along all of those paths, looking for paths that are the slowest, the ones that have the most congestion. And what we do is we send what we call ultra high priority feedback to the source to modify the weighting of those paths. We still want to use them, we still want to be able to probe them. We want to use the most congested ones the least for 2 reasons. One, of course, is there's less bandwidth available, and 2, we want to help relieve that congestion. And so, of course, there's move forward. There's the in-order delivery to the host, but then also, as importantly, is we have end-to-end flow control. So there's a very complex state machine ensuring that we're always maintaining optimum performance across those 8 parallel paths. Next advancement I want to talk about is our deadlock-free routing. So for those who aren't familiar, network deadlock occurs when multiple paths have a cycle of dependencies. So all these paths are trying to move through the network, and buffers are blocked. You can't deliver packets because every single path is blocked by another path that can't move. That's, of course, very bad in the network. To recover from a deadlock, you typically have to flush queues, you lose packets, huge spike in latency, workload performance is impacted. So the routes that we calculate are deadlock-free. So we have a patent-pending algorithm that runs on a distributed fashion. So there's no central authority that's scale limited. This algorithm runs in a distributed fashion on the resources of a network card. So again, scales very, very well. And this has a couple of characteristics. The first is we ensure high path diversity. Other approaches to deadlock-free routes typically reduce the number of available paths with the network. We ensure we have 8 available paths, which allows us, of course, to use all of our adaptive routing. And also it works in complete or sparse topologies. So you can have a completely populated network, you can have nodes missing, there can be link failures, there could be node failures. And as you get to larger and larger scale, the odds of there being a failure somewhere in the network, a power supply failing in a server or maintenance occurring is very, very high. So it's very important that your routing algorithm doesn't just work in a perfect network, but in particular works very well in what you can call ugly networks, networks that have real world problems. And of course, our algorithm does that. And the way it works is we have 12 virtual channels on all of our physical ports, and we divided them into 4 layers. And as we're generating the source routes at each node, not only do we have a path through the network, but we assign a layer to those paths. That ensures that all the cycles of dependencies are removed from those routes. Again, any topology, failures or no failures in a distributed fashion with high path diversity. Very, very important as you're getting to scale. A key element of Rockport is about maintaining latency performance for the critical messages. So a lot of workloads will send critical small messages that are highly sensitive to latency. You can think of these like a barrier message as an example. And where there are delays in these messages, the workload will slow down. So what we've done is designed into our solution the ability to identify critical small messages. There's a couple of ways we do that. And what we're doing is ensuring that they're almost immune to congestion. If you look at the switching performance of our solution unloaded, when you compare it to a fully loaded switching element under very heavy load, there's only 25 nanoseconds of additional latency per hop. So even when there's small bursts of, microbursts of congestion in the network, we still maintain the latency performance. There's a couple of ways in which we identify those critical messages. It's explicitly available through MPI libraries and middleware, as example, an upcoming version of MVAPIC2. As well, we're adding heuristics into our RNOS to detect which messages are critical. So we'll work with all MPI libraries. So if you combine these different techniques, what we're trying to do is understand the traffic patterns generated by the codes, understand what their requirements are. Is it bandwidth sensitive? Is it latency sensitive? Or is it sort of balanced requirements? And applying the right network techniques to that kinds of traffic in order to ensure the performance they want. So bandwidth sensitive traffic, adaptive multipath makes a lot of sense. Latency sensitive traffic, obviously ultra high priority, is designed to maintain latency performance even under heavy load. And all other traffic, we typically use the 4 shortest paths. So making use of these paths optimally to match for workload requirements. So why are some of these things important? Well, if we contrast ourselves with a traditional high performance network, you take a look at the path here from A to Z, with per destination routing, you'll end up with a single path through the network for all traffic going to the same destination. And so anywhere along that path, if there's any kind of congestion, what you're going to see in that path performance is reduced bandwidth and increased latency. So if you have bandwidth sensitive traffic, you're impacted by the amount of bandwidth you have. If you have latency sensitive traffic, well, you're going to see additional latency through the congested switch port. And so on the Rockport side, because we're distributing the traffic, because we're doing that on a per packet basis, we're really ensuring that we don't have hotspots. If there are hotspots, we can avoid them, and we can immediately react in hardware if there's any kind of local or remote link issue. Oops, not moving. There we go. So the other issue we see in traditional networks is the stranded bandwidth, I'll call it. This is how much effective bandwidth you actually have in a network. So if we're running a multi-node job here, and some of the nodes are remote, we're going to be using some of the uplinks in the network, some of the spine bandwidth. And the challenge is, as they're communicating, there's always an uneven distribution of the load on those links. It's just normal statistical clumping. So we get the flows unequally spread across the available uplinks, which means some of those links will be very heavily utilized, and some of those links may even be completely idle. This happens more as you get to larger scale. So effectively, you don't have available to you all of the uplink bandwidth available from those switches. It's stranded resources, which means you can get lower bandwidth performance, you're going to get higher latency, which of course is detrimental to all workloads. Because we're distributing the traffic and we make use of all of the bandwidth in our network, we ensure that you get very efficient use of that 300 gigabits per second of network capacity. And we're adaptively adjusting the loading based on the real-time end-to-end full path congestion information. So I mentioned before about the advantages of our inter-rack connectivity, those 6 links that don't stay within the rack, but connect right across the cluster. And the reason that's important is as you get to, if you're in a large cluster running lots of jobs, the servers, the nodes become fragmented. As you're running more and more jobs, the servers that become available to you when you want to start a new job will be distributed across the cluster. It's very unlikely you'll have the right number of servers become free within the same rack environment. So what that means is in a traditional switching environment, your performance on the same switch is usually very good. Your performance across the network is much, much worse. But because you're almost guaranteed to have servers that are not in the same rack as you, what you see is that the inter-rack performance that is the bottleneck for your overall workload. Because what Rockport has are direct links between racks, that physical placement issue doesn't really exist. The performance in our solution in the rack is really equivalent to across the racks. So especially in a multi-workload environment, we're able to much better make use of the bandwidth available in the network, as well as provide consistent performance regardless of where the job is placed. When we take a look at some of the quantitative measurements of what this means, we have our flip switching. We break packets into small pieces, but critical messages become immune to congestion. Again, only an extra 25 nanoseconds per congested switch hop. And when we compare that blocking time with other high-performance network technologies, Rockport's at 25 nanoseconds. What you see in an InfiniBand switch, as an example, is 15,000 nanoseconds of blocking time potential. And in an Ethernet network, you see 220,000 nanoseconds. So the ability to maintain performance under heavy load really drives consistent workload completion times. And we'll get into some customer workload results in a second. But here we're using the OSU latency, the point-to-point latency micro benchmark, showing the performance for Rockport under load and InfiniBand under load. So what we're seeing here is the first 64 bytes in message sizes have been identified as ultra high priority. So you see them have a very consistently low latency. And then we have the messages greater than 64 bytes, making use of those 4 shortest paths. So there's a little distribution of the latency as we're doing 20 different runs of a benchmark. When you contrast that with InfiniBand, you can see in the half round trip time latency on a single congested port, a big spike in latency and high variability of performance, which of course makes it very challenging to predict workload completion time. I want to share some customer workload results. The first is AI machine learning. Audience is probably very familiar with BERT. So this is a small scale cluster. It's only 10 nodes. But the key is that the nodes are connected across 3 switches on the InfiniBand side. So it's a small scale multi-switch environment, because what our customers are wanting to do is do small scale experiments to see what the performance would be at larger scale. So multiple switches are really important. And so we have an undersubscribed spine. There's more bisection available than the nodes can inject. And so this is an unloaded test. This is simply running the workload on either 4, 7, or 10 of these nodes, again, spread across the multiple switches. We contrast that with Rockport, and you can see that our workload completion time is between 24 and 38% faster, even at small scale, because we're much better at effectively providing access to the bandwidth of the network. Workloads complete faster, simply because we're better at moving traffic through our high path diversity. And we recently did another experiment. This is WRF, run by a partner of ours on Frontera during recent Texas Scale days. Those unfamiliar with Texas Scale on Frontera, there's a dedicated set of nodes here. So this is an environment where typically there are tens of jobs running. When the nodes that we had, there are no other nodes on the same part of the network. So it's a dedicated cluster environment for us, high performance nodes, of course. And we ran WRF. It's a 3-hour simulation, pretty standard CONUS data set. We ran it on 14 nodes up to 112 nodes. And what you can see here is Rockport has a workload completion time even on the unloaded network. And the key is as the scale gets higher, the performance advantage also grows. So what Rockport is really good at is helping code scale higher, getting better performance, ensuring that workloads can actually run better, when we're ensuring we're avoiding self-congesting the network due to large scale of the application. Then for those that we made an announcement, I think it was about a week ago, Durham University has selected Rockport as part of our exascale modeling. And we've been testing our environment for about 1.5 years, so our very good workload completion time advantages. They saw 28% performance improvement in their experiments. And so really focused on using Rockport to try to, again, scale their codes as they prepare for exascale in the UK. So just to summarize, what Rockport's about is accelerating and providing predictable workload completion times. We're a high-performance network. We see ourselves as a very powerful alternative compared with InfiniBand or high-performance Ethernet. We're very good at providing access to the available network resources, and that's key, because that's usually the bottleneck that slows down applications, and it gets worse at scale. So the bigger the scale, the bigger the challenge you have of providing access to network resources. And it turns out that we're also a green technology, lower power, lower carbon footprint, even lighter weight to ship, as there's no heavy switches involved. And we've simplified the operation of a network. So even as these technologies at the other end of the scale are adopted by the enterprise, very easy for them to deploy and use our solution. So that's the end of a presentation. Any questions?
We have time for a few questions.
Just quick. One quick question. So over the course of the day, we have seen talks from various vendors. So one thing that I noticed was that several vendors, including Rockport, was trying to, let's say, split up the packets into flits instead of sending it out as MTUs. So are there similarities and differences in the approaches, or are they all like fundamentally the same basic approach?
Well, what we're trying to do is the edges of our network, we want to be very compatible with other network technologies. And if you think of the broad set of IT elements available and used within a cluster, Ethernet is the protocol of choice. So wherever you're accessing it from. So we think it's very important to maintain a standard protocol on the edges. We take the advantage of the FLIT architecture, which is used by multiple vendors. It's a proven technology, but we do it in a different way in that we still have Ethernet frames. So you can think of the edge of our network having a standard network sitting there. We want to be able to forward those original frames across the network. So there's a performance advantage, there's a software stack advantage, there's even a familiarity advantage. You know, a lot of people adopting performance intensive applications don't understand anything but Ethernet. That's really all they do every day. So having a familiar technology is also an advantage. You know, there's lots of ways in which people can leverage different networking technologies. We believe FLITs make sense. We also believe Ethernet makes sense on the host side.
Thank you.
Any other questions? Yes, just 1 minute.
I was just wondering if in the test that you ran, you showed some of the students, you would InfiniBand that you enable any adaptive routing capabilities at all. You seem to talk about very static routes, which is not current InfiniBand technology at all.
Matthew, did you check the question?
Yeah, I had trouble hearing that. I'm sorry.
Yeah. The question is, when you compared with InfiniBand, did you turn on the adaptive routing feature of InfiniBand?
Sure, happy to talk to that. So this is, you know, a large scale. It's now 16th on the top 500 list. So they've set up their IB network optimally for that scale and the kinds of workloads they run. And in this case, you know, there was no congesting traffic. So we don't have access to change how our customers use their existing high performance networks. So typically what we see are customers saying, well, this is the network I have today and the features and capabilities that make sense for me. And then of course with Rockport, it's what we recommend being used. And you know, adaptive routing is an interesting concept, right? It's an umbrella of multiple technologies. It's, you know, change the route for all the same things in the route table to another route. And it's like a big chunky switch where you move from one path to another path. And really all you're doing there is exposing that traffic to the congestion along the other path. With Rockport, because we're concurrently using 8 paths on a per packet basis, we're really able to do fine-grained adaptability, really spread the load. So you know, we see similarities, we see in adaptive routing techniques, we see advantages in what we do. But typically when we're doing these, when our customers, I should say, are doing these sorts of workload tests, it's how they run their existing network. You know, they've tried some of the other capabilities. For some customers it may work well, for others, you know, in this case, you know, may degrade overall performance if you use them. So it's, you know, we let our customers decide how to evaluate the solution. These are based on our partners and customers running these applications.
I would just point out that the characterization of the adaptive routing algorithm is far from correct. So it's.
Can you speak a little bit closer? I think.
Sorry, it's a little hard to hear. Very far away.
Is this better?
Yeah, that is better.
Yeah, I would say with current technology and even older technology, adaptive routing is a packet by packet basis, hop by hop basis. There are no a priori determined routes and the like. So it's adaptive based on traffic, and it's adaptive based on the condition of each of the hops along the way.
Yeah, well, what we've done is, you know, obviously a different approach. We're source routing based. So what's important is to monitor the aggregate congestion along the paths. That's really what's going to drive your performance. So we're using the 8 paths. We're monitoring the congestion performance and adapting the load on each of those paths based on what we're seeing. And this tends to be, the feedback is within a round trip time. And because we're using our ultra high priority technology, you know, that's usually a 2 microsecond, 3 microsecond response time. which means we can very quickly respond to micro-congestion events. And even when they occur, allow us to maintain ultra-high priority, of course. So it's a different approach. The way we've architected, we believe source routing makes a lot of sense because there's information you can collect along all of the paths and then known paths. Yeah, we've seen very strong performance results using our multipath technology. It's been deployed at Frontera. We're seeing some very positive results.
Okay, any other question?
I think that's about it. Thank you, Matt.
Thanks a lot again.
Thank you very much.